Right, welcome everybody, and thank you for joining us for this new webinar. Today we will talk about implicit conversions in C, the hidden enemy. I am Lavinia Battaglia, CSR at BUGSENG, and our speaker is Roberto Bagnara, who, long story short, is CTO at BUGSENG, computer science professor at the University of Parma, member of the MISRA C working group and of the International Standardization Working Group of the C programming language. Before we start, please note that you can write all your questions in the Q&A section throughout the entire webinar, and then we will read them and reply at the end. All right, then, let's turn this over to Roberto.
Okay, thank you very much. So let's start with this webinar of today, which is, I think, very interesting and very instructive. So here is the outline of the webinar. I will start with an introduction to the problem. Then, in order to explain implicit casts, I have to review explicit casts a little bit. And so the section on implicit casts is the main one. And then I will go to draw some conclusion. So let's start with the introduction. The subtitle of this webinar is a hidden enemy. So to explain this, I have prepared an example. So suppose that a freeze alarm is meant to protect your house with this code. A freeze alarm is a device you would put in your house that in case the temperature goes too low before your pipes freeze and thus risk bursting, will do something. For example, it will switch the heating system on. So this is the code. Okay, sounds reasonable. So freeze alarm should return true if and only if the temperature in Celsius degrees goes below the minimum temperature that you have set. Now, suppose the minimum temperature you have set is 1 Celsius degree, which is fine because pipes will freeze around -6, -7. And however, if you make the hypothesis that there are the following temperature readings, so 5, 3 degrees, 2 degrees, 1 degrees, -1, -2, -7. Okay, and at this stage, you have frozen pipes and they burst. Can you spot the hidden enemy? So the hidden enemy, of course, is an implicit cast, which is playing against you in this case. Can you spot it? Okay, the title couldn't be too long. So the other side of the hidden enemy, something that exists but you don't know, it does, is the imaginary friend. So you imagine something would save you. However, this doesn't exist. So here is another example. So John wants to compute the average of two 32-bit signed integers. And of course, he knows that the sum of two 32-bit signed integer can be larger to be represented in 32 bits. So he uses 64 bits to represent the sum. And here is the code. However, computing the average of 2 billions with 2 billions, which should be 2 billions, in reality return 666. Can you guess what is John's imaginary friend and where it is? Okay, here is the first poll. So I will give you a minute before Lavinia posts the poll. So try to spot the hidden enemy in the first fragment and the imaginary friend in the second fragment. Again, in the first case, you should look for an implicit cast that is there, but the programmer didn't know it was there and how did it work. In the second case, the programmer was counting on a cast that is not there. Okay, let's go with the poll.
So could you spot the hidden enemy and the imaginary friend? Okay, so 41%, yes, both of them. Well done. 35% only the hidden enemy, 9% only the imaginary friend, and 5% none of them.
Good. So we will explain these examples in detail through this webinar. So now, suppose we have a language which is not C. It is just like C, but without implicit casts. So every conversion would have to be explicit. It would be verbose. It would be boring to write program. You should always write the casts you need explicitly. However, it would be safer because what you see is what you get. So the conversion would always have something in the syntax to indicate to you, I am here. Then maybe you don't know what the conversion is doing exactly, but at least you know it is there. So, however, C is as it is. It's a compromise, okay? So it's a compromise. It's not meant to be a verbose language, and it's not meant to be safe unless you actively work to use it in a safe way. So there are basically two options. You either stick to MISRA C and use a good tool, and which is the topic of the next webinar in 2 weeks from now, or you learn the C rules governing implicit cast so as to always know where they are and what they do. So in this webinar, we explain this, point 2, okay? And from this, it will be clear that solution 1 is actually much better. So let's start with explicit casts. So what exactly does a C cast do? This is a general case, rather general case. So we have a type T, variable destination of type T, and a cast to T of SRC. So without having detailed information about what T is and what SRC is, we cannot say much about what this piece of code does. Actually, we can say nothing. So in order to explain what this C cast does, we will resort to the C++ cast. In C++, the casts, the different casts have been separated. They have a different syntax that is explanatory of their purpose and of their intended use. So in order to explain the C cast, we will have a very brief introduction to the C++ cast. So you might wonder if this is legitimate. And yes, it is, because in C++, in the C++ standard, it is stated clearly that if an assignment of this form compiles in C, then it has the same meaning in C and C++. So let's start with the static cast. Static cast is a keyword in C++, and this can be used for any normal conversion between types. What do I mean by normal conversion? A conversion where there is a more or less defined value conversion between one type and another. This includes all casts between arithmetic types, cast of pointers to and from void pointers, and cast between enumerations and integers. No runtime checks are performed, so no check is done to make sure that the data fits in the new type, or in case you are converting pointers that you obtain a valid pointer. Okay. Static cast cannot remove the const and the volatile qualifiers. To do this, there is the const cast. The const cast can be used basically only to remove the const and or the volatile properties from pointer. And the target data type must be the same as the source data type, except the removal of one or both qualifiers. I am simplifying, of course. So in C++, which is a more complex language than C, the explanation would have to be longer than this. Then there is the Reinterpret Cast, which is able to perform conversions in many more cases. Basically, the Reinterpret Cast is a way of specifying the reinterpretation of a bit pattern according to a different type. So in particular, you can use it to convert between any kind of pointers or to convert between integer and pointers. Okay. The Reinterpret Cast keyword cannot remove const or volatile qualifiers, and again, there are no runtime checks whatsoever done to ensure that the data fits in any sense the new type. So a C cast, in order, tries to do the following. First, a const cast, and if this is valid, then this is what is done. Or a static cast, or a static cast followed by a const cast, or a reinterpret cast, or a reinterpret cast followed by a const cast. The first that applies is the one that is chosen. If all of the alternatives fail, then the conversion is ill-formed. So time to move to implicit casts. Here is an example that you can use with your favorite compiler, and most compilers will give the expected result. What is this? It's an example program that will trigger compilation errors, because you see in all these assignments, we are converting something that is numeric to a struct, and this is a conversion that is invalid. You see, it doesn't make any sense. So it's an error, and every compiler will flag the error. The majority of compilers will do more than simply flagging the error. They will tell you what is the type that you are trying to assign to u, the variable u. So you can use this program in order to experiment what the C standard is saying. So what is the type of plus A? A is a variable of type signed char. However, plus A has a type that is different. So let's, in order to understand what are the types of plus A, of tilde B, or minus C, and of D shifted left by one position, we need to understand some concept. First, we need the concept of integer rank. So this is a quote from C99, but other versions of the following versions of the C standard are basically the same. So every type is characterized by a rank, so every integer type. And when the rank of one type is smaller than the rank of another type, then the type with a smaller rank is a subrange of the values of the other type. So the type with a smaller rank can represent a subrange, so not just a subset, but a subrange, meaning it is a continuous sequence of integers without holes. Okay, so here are the rules that are set forth by the C standard for integer ranks. So no two signed integer types shall have the same rank, even if they have the same representation. So as we will see in a minute, even on machines where int has the same number of bits as long, they have a different rank. The rank of long is higher than the rank of int. Okay? So there are Other rules, long is a greater rank, char as the smaller rank, bool is even less than char, and so on. However, to make it short, so I have prepared a summary. So let's forget about extended integer types that an implementation can provide. So an implementation, for example, can DSPs, for example, are typical examples of this situation in which you may have additional integer types. So let's take the standard thing here. So the rank of bool is strictly less than the rank of char. Char, signed char, and unsigned char have the same rank, which is strictly less than the rank of short. Notice that the signed and unsigned version of a type always have the same rank. So, for example, the rank of short is equal to the rank of unsigned short. Okay? The rank of short is less than the rank of int, which is less than the rank of long, which is less than the rank of long. Okay? So this is the first concept we needed. And now we need the concept of integer promotion. So the rule for integer promotion is actually very simple, and it is this. If an int can represent all the values of the original type, then the value is converted to an int. Otherwise, it is converted to an unsigned int. Okay, integer promotions are applied, among other things, to the operands of the tilde operator, of unary plus, of unary minus, shift operators, and to the either binary operators only when the operand is an integer with rank less than the rank of int, or it is a bit field. So things that have types that have a rank higher than int, they are not subject to integer promotion. So only shorts and chars are subject to integer promotion. Long is not subject to integer promotion, and int is not subject to integer promotion, and the same as long. Okay, so the rule is very simple to remember. The expression type becomes the first type that can contain all the possible operand values in the order. Int, so if int can contain all the possible operand values, then int will be chosen, otherwise unsigned int. Notice that I have written in red all possible operand values. So this is a static decision. It does not depend at all on the actual value you have on a certain expression at runtime. Okay, if the static type, it's a decision that is taken on the static types. Okay, so now we know more. Okay, so what are the types of plus a, tilde b, minus c, and d shifted by 1? These are the types. So let's try to go through them. Okay, we have plus a as type signed char. Can int contain all values of signed char? Yes, on any architecture. So plus a as type int. For tilde b, the situation is different because we have two options. We will go through them in the next slide. Okay, so tilde b is unsigned short, and tilde b will either be int or unsigned. Let's go on. Minus c. So c is long, no integer promotion, minus c is long. Okay? And d D is unsigned, so the rank is not less than the rank of int. It is actually equal, so no integer promotion again. And the type of D shifted left by one position is unsigned. So let us look at the problematic case. Why, under the declaration unsigned short b, tilde b can have either type int or type unsigned? There are two cases. First case, when unsigned short values always fit an int, then it will be int, because this is the integer promotion rule. So if it fits an int, choose int. And this is the case, for example, for Intel architecture 32 bits and many other architecture where shorts have 16-bit and ints are 32 bits wide. Okay? So all values of type unsigned short will fit into int in this case. But this is not always the case. For example, there are several 16-bit architectures where the short and the int type have the same number of bits. For example, 16 bits. So this is the case of C2000, to mention one reasonably modern architecture, but Z80 would be another example. Okay, here, since not all the values of type unsigned short can fit in int, then b is promoted to unsigned, and so tilde b will have type unsigned. Integer promotions are easy. Now we go to usual arithmetic conversion. So let's start with the floats, floating point types that are easier than integer. So the usual arithmetic conversions are a set of rules that are used together with integer promotion to find the resulting type of expression. So for the floats, it's easy. Once you have recalled that long double is larger than or equal to double, meaning that long double is a superset of double. So any value of type double can be converted to long double without any loss of precision. And similarly, double is larger than or equal to float. The rules are very simple. So if both operands have floating point type, then the operand with the smallest type is converted to the type of operand with the largest type. So it's safe, okay? Which is good. And the other rule, if only one operand has floating point type and the other is an integer, then the integer operand is converted to the floating point type. Okay, here someone might think that the other way around was also possible. In fact, it was. Okay. However, converting an integer to a floating point type is less likely to cause problems than the other way around, because the range of floating point types is usually much, much larger than the range of integers. Okay, so these are the usual arithmetic conversions for floats. Let's go to the integers. So the usual arithmetic conversion rules are as follows. First of all, if both operands are integer numbers, integer promotion is applied to both. Okay, so at the end of this first stage, the least ranks that you can have are int and are those of int and unsigned int. So anything below this will be promoted to either int or unsigned int. And then the following steps are followed. And the first three of them are safe, meaning that there are no risks involved. Only the last two steps are risky, and because there may be a loss of sign and of the value and bad things. Okay, so first rule, easy. If the operands have the same type, that is the type of the result. Second rule, if the operands have the same signedness, meaning they are both signed or both unsigned, then the lower rank type operand is converted to the other operand type. Okay, again, this is very reasonable. Okay, so you convert in the direction of safety. If the signed operand type can represent all the values of the other operand type, then the unsigned operand type is converted to the signed operand type. So here you also have an explicit guarantee that the conversion will be okay. Okay, because you apply step 3 only if the signed operand can represent all the values of the other operand type. Then step 4, if the unsigned operand has greater rank, then the other operand is converted to its type. Okay, so we will go back to this. Otherwise, both operands are converted to the unsigned integer type with the rank of the signed operand type. So looking at this list, one might think, why does WG14, the standardization committee for C, hate us all? Well, no, because you see, the things are in order. So the first 3 rules are safe. The 4th and the 5th rule, you see that they favor the conversion to unsigned. Okay, so you may have wraparound, but not nastier things. Okay, so these are the rules of usual arithmetic conversions. We will see examples now in order to make sure we understand the thing properly. So we use the same technique as before. So we write a small C program where we write illegal assignments of arithmetic types to a struct in order to trigger a compiler error that probably will give details about what is the type. Okay, so what are the types this time? Let us go through these 6 examples. So the first one is simple. It's a float. F is a float plus a long double. So they are both floating point types, and the rule says that we will take the largest. So F plus GD will have type long double. Float will be converted to long double, and then the addition will take place in long double. The conversion of F to long double is completely safe. Okay. Then second example, we have seen that when we have a floating point type and an integer type that are combined together with a binary operation, then it is the integer that is converted to the floating point. So I will be converted to float, and the addition will take place in the type float. So float plus float will be a float. Here we have an integer I, and we have an unsigned long G, an integer I and a long G. So this also is easier. They have the same signedness, and so the operand with the smallest, with the type with the smallest rank, which is the int 1, is converted to the type of the other one. So I will be converted to long, and this is an addition that will take place in the long type. Here we have float plus UG is unsigned long, we have seen that integers are converted to the floating point type in this case. So UG will be converted to float, and this will be float plus float, which is float. The fifth case is tricky because depending on a reasoning we'll go through in the next slide, the result may be either long or unsigned long. So let's postpone this for a few seconds and let's analyze the sixth example. Here we have int plus unsigned, and int plus unsigned gives unsigned. So this I will be converted to unsigned. Can things go wrong or in a way that is not expected? Yes, because I may be negative. We will see this later. So why under the declarations long G and unsigned short US plus G can either have type long or unsigned long? There are two cases. The first case is that unsigned short values always fit in int. So US, the unsigned short, is promoted to int, in which case this will become int plus long, same signedness. We use the type of with the highest rank, so long. So we will have long plus long, which gives long. An example of such architecture is Intel Architecture 32, also called x86. Okay, very common. The other case is when unsigned short values do not necessarily fit in int. So US is promoted to unsigned int. And this splits into two further cases, because the first subcase is that long can represent all the values of unsigned int. So we have unsigned int plus long, and by one of the rules we have seen, since long can represent all of the values of unsigned int, this will give long. So unsigned int will be converted to long. We will have long plus long, and the result is long. An example of architecture is a C2000 that has 16-bit shorts and ints. They are both 16 bits, and long type as 32 bits. And the other possibilities is that long cannot represent all the values of unsigned int. So we stumble upon the last case, the fifth case. So both are converted to unsigned, to the unsigned type with the highest rank. So unsigned int becomes unsigned long, and long becomes unsigned long. So we have unsigned long plus unsigned long, which gives unsigned long. This is perfectly valid, and there are, as an example of architecture, let's take the S12Z, and there are options in the Code Warrior compiler that allow you to have short, int, and long, all with 32 bits. Okay. So here is another example of usual arithmetic conversion, and then this is meant to explain how things can go wrong. So if you ask yourself, what will this program print? Then the answer is surprising, maybe, because it prints false. Because the expression I less than UI goes through all 5 steps of the integer usual arithmetic conversion. So let's go through them. We have int and unsigned int. They are not the same type, so the first rule doesn't apply. They don't have the same signedness. One is signed and the other is unsigned. So they don't have the same signedness, and the second rule doesn't apply. int cannot represent all the values of unsigned int, of course. Okay, so the third rule does not apply. They have the same rank, so the fourth rule does not apply. And so we stumble upon the fifth rule, which means that int will be converted to unsigned int. And in this example, the int I is -1, meaning that, I don't know, if in any case, -1 converted to unsigned int will become a very large number. So if the implementation we are using is using the 2 complement representation for negative number, we end up with a pattern of all bits set to 1. For example, if we have integers of 8 bits, -1 would convert to 255. If the implementation uses the 1 complement representation for signed integers, then the pattern of bit will be all 1 and the last bit will be 0. So this would be 254. In sign and magnitude, the representation of -1 is 1, all zeros, and the final 1. So on 8 bits, this would be 129. So in any case, we end up with a large positive number, and the comparison doesn't give the results we expect. Okay, so here is the second poll. So are you surprised? How do you feel now? So if I take the occasion to signal the next webinar, well, we will show solutions to this problem. The next webinar will be in 2 weeks. It's the essential type model of MISRA C 2012. Here you see the registration link, but all links will be sent to you by email after the webinar, so don't bother to write it.
Okay, so a 13%, not at all. It is all very familiar to me. The majority, in fact, the 66%, somewhat. I knew there were dangerous pitfalls in this area. 7%, yes, I am. I was not aware how serious this problem is. At 2%, I'm actually scared. At 7%, yes, no, who cares? I'll always comply to MISRA C.
Okay, very good. Okay, so it's time to go to the conclusion. So let's look back at the hidden enemy. So to make sure that you see what is my solution to the quiz. Okay, so again, we have this freeze alarm code, and as I've said, if these are the successive temperature readings, then freeze alarm will never be true. So the alarm will be false, nothing will be done, and our pipes will freeze and burst, and this will be a lot of damage. So the question was, can you spot the hidden enemy? And here it is. Okay, we have seen it a couple of slides ago. So here, the temperature C variable, which is of type int, will be converted to unsigned. So when the temperature passes from 1 to -1, okay, here we will have a large unsigned quantity, and the comparison will give false. So the freeze alarm does not trigger. Let's also look at the imaginary friend example. So again, the problem was the problem to solve was to compute the average of 2 32-bit signed integers, and John, to avoid the overflow, used a destination variable for the sum, which is 64-bit wide. Okay. However, the result was not the one that was expected. So the question was, can you guess where is John's imaginary friend? And here it is. Okay. John made the assumption that since the destination type for the addition was 64-bit, made the assumption that the language would insert an implicit conversion of X and Y to 64 bits, so that the addition could take place in 64 bits. Whereas this is not true. This is an imaginary friend of John. So X plus Y, the addition will be performed in 32 bits, and maybe it will give rise to overflow, which is undefined behavior. So actually any number can be returned, including 666. Okay, so this is what I mean by imaginary friend. So it doesn't really matter, as you have seen from the rule, what you do with the value afterwards. The fact that you are storing the value into a 64-bit variable doesn't matter at all. Okay, so good. So time to conclude. In this webinar, we have gone through the semantic of explicit casts in C and also to some extent in C++. And then we have seen the semantics of implicit casts in C, and in particular, we have seen the rules for integer promotions and the rules for the usual arithmetic conversion. There are, as always in this series of webinars, important messages to take home. Implicit conversions are tricky and dangerous. So you can really make a lot of damage because of implicit conversion. And moreover, implicit conversion are strongly dependent on the implementation defined aspects of the language. So the sizes of the integer types, the signedness of plain characters. So if you always work with the same C dialect, so you always work with the same target, same compiler option, then you are in better shape. So you will develop with time a skill to guess where is implicit conversion and what it does. But otherwise, it is much better, much better, as we'll see in next webinar, to enforce MISRA C with a good tool, so that the tool will prevent you from doing potentially dangerous mistakes because of implicit conversion. Okay, so if you have questions.
Are there other kinds of implicit conversions in C besides integer promotions and usual arithmetic conversions?
Yes, there are other implicit conversions in C. I didn't cover them because they are, say, less dangerous. So, for example, in return statements, the value expression is converted to the function return type. In assignments and initialization, the right-hand side of the assignment or initialization is implicitly converted to the type of the left-hand side, so the variable or object you are assigning to. And also in function calls, the arguments of the arguments are converted to the type of the parameters if they are declared, as they should be in most cases. If they are not declared, there is a mechanism called default argument promotion. So it consists in integer promotion. So in the rules that anything with a rank smaller than int will be converted to int if int is able to contain all the values. Otherwise, it will be converted to unsigned int. And also, float will be converted to double in default argument promotion. So these are basically the other classes of integer promotions.
Okay, next question. To replace implicit conversions with equivalent explicit ones seems to pacify most checkers. Is this a solution to the kind of issues presented in this webinar?
Well, no, because it is perfectly possible to write the wrong explicit cast. So in general, when you do something just to make a checker silent, you are doing a mistake. So if you, for example, if you substitute all implicit cast with explicit cast, you may very well have a hard time spotting the real issues. So your real friends, okay, in contrast with the imaginary friends we have been talking about. So no, this is not a good solution. So if you add cast without motivation, it may well make things worse. This is probably a good topic for another webinar, but as you will see in a couple of weeks, MISRA C is actually, in my opinion, the good solution to these kind of problems.
Okay, very well. Thank you, Roberto, and thank you again, everybody, for joining us today. Of course, if more questions come to mind, you can always drop us an email at info@bugseng.com. As I said before, our YouTube channel is in general a good informative spot. We covered many topics over time, and we also upload very useful demos of our static analysis tool, Eclair, which of course we invite you to try. If you enjoyed today's webinar, don't miss out on the next one, as it will show you that sticking to MISRA C and C++ is much easier than trying to remember the complex rules that govern implicit conversions. We'll discuss this on July the 30th in the webinar called The Essential Type Model of MISRA C 2012. All right, we will send you the link to register the post-webinar mailing, and thanks again for attending. We hope to see you all next time and hear from you very soon. Bye-bye.
Bye-bye.